All right, so I think everyone is in. So we are ready to start the grand finale of our CTEQ 2025 summer school. Now, this is still not the end of the full program. So tomorrow we'll talk about multi-clouds and the machine learning. But let me quickly re-emphasize the meaning of CTEQ. So CTEQ stands for the Coordinated Theoretical Experimental Effort, or QCD, and the related subjects. And so this idea of coordination between theory and experiment, and now also increasingly with statistics, is as relevant as ever. So of course, CTEQ was started in the 1990s, around the time when the Tevatron was doing the first measurements, and we had to understand what these measurements mean. But we have the same kind of need for the cross pollination of theory and experiment in the high luminosity LHC era, and not just between the LHC experimental theories, but also cross pollination with other experiments like the electron collider or fixed target experiments. And so our last speaker in this part of our meeting is a very distinguished and experienced participant in this whole process of working on understanding the data. And so it's my pleasure to introduce the MSc Distinguished Professor Chip Brock. Now, I think, well, first of all, we are very grateful that you are able to find time to come to talk to us, but of course you also were present at the previous lectures. And I think we were looking for kind of a summary of what has been going on, but also for your vision towards the future. And so this last talk will be based on the vision, which is kind of broader than the topics that we discussed. Now, the reason I think is Chip is particularly well positioned to give us some reflections is that, well, according to his CV, he has multiple experiences, not just in experiment. So Chip, of course, is a member, well, for many years was a senior member of D0, and so now it's the Atlas collaboration. But also Chip, well, according to his CV, he got a bachelor degree in electrical engineering before moving towards the master degree in physics and philosophy of science. And so we need to think about philosophy of science and what do these measurements actually mean in the grand picture of things. But then, of course, also Chip got the PhD in both particle physics, both experiment and theory. So I think you are one of my closest collaborators who worked on some theoretical calculations like points of external summation for Brilliant processes many years ago. And then Chip also served with several very important positions, such as, of course, Chip was the chair of this department for many years, and he was a member board of directors of the Formula Research Alliance. He was the chair of the U.S. Atlas Institutional Board. He was the chair of the division of particle and fields in the American Physics Society. So Chip has a great vision of what's going on, and he will tell us in the next few minutes. So please go ahead.
You guys are making me tired.
I make you tired, yes. So.
Okay, it's not working.
You have a lot of questions.
There, you must be tired. In fact, the Indico page makes me tired. I appreciate an introduction. I mean, I'm from the LAC, and so I appreciate it when anybody recognizes me at all. The insecurity that comes from getting together for 20 years with 3,500 of your closest friends can kind of get into your head. In fact, I was at a conference on campus a few years ago where I discovered that I was a university distinguished professor. And so I have been worried about whether my teeth going to work in my bar. So I'll ask for a vision talk. Well, I'm pretty prejudiced, but I think it's not unfair to say that we pretty much have a vision of particle physics, either directly or indirectly, through the discovery of the Higgs boson. So when I'm done, I'm going to take you through a pretty high level what I hope is entertaining. You put your pencils away, I used to say, you wouldn't do that now because you have pencils. But it's partly history, what I'm gonna do, partly summary, what I'm gonna do. Partly entertainment, what I'm gonna do, I hope you'll smile a little bit. And then when I'm done, I hope you'll go storm the barricades against the standard one. Because my theme here is that there's still stuff wrong. So I'm gonna start with a physics civics lesson. Because you're all young professional physicists, many of you in the United States, I'd like you to know a little bit about how we belong to comply in the United States and how we are professionals together. I think there are features of the standard model that are untenable. If you ask anybody what's wrong with the standard model, you'll get that: matter, antimatter, asymmetry, and gravity. I think it's sure, but I think it's a whole lot more subtle than that, and I'm going to take you into some of that. I'm just a country physicist, and so I have my own particular views about these things, but I hope you'll find it entertaining and maybe thinking about it, and then how the Higgs boson informs our next steps. So, planning in particle physics, not just in the US, but everywhere. In fact, this is a big week in particle physics. Your professional society is the American Physical Society, and particle physics lives inside of one of the many divisions. We hold hands with the Physics of Beams Society. Buried in there is the astrophysics, the division of astrophysics, and sometimes even the division of nuclear physics. Governments ask their professional societies what's the right thing to do. Governments used to ask their professional societies what's the right thing to do. I'm completely unnormalized now, but it is certainly the case that planning in particle physics and other branches of science comes from within. We have two vehicles where particle physics is the future of particle physics is considered. One is called the SNOMAS. SNOMAS studies are organized by the Division of Particles and Fields. They've been around for a long time. Sometimes they're very particular. They have been in the past very particular to particular questions. Sometimes they've been comprehensive to the entire field. The last comprehensive one of the normal ad hoc sort was in 2001. But then in 2013 and 2021, we did something entirely different. The other vehicle is a tortured acronym called the Particle Physics Project Prioritization Panel. Sounds pretty governmental. We call it P5, of course. It's the official organ of the advice structure to the National Science Foundation and the Department of Energy. And it comes through a committee called the Energy Physics Advisory Panel. So the history of this is that there have been ad hoc P5s. There's a P5, there's a P5, the blues are P5s, and Europeans do the same thing. And in particular, Europeans this week are meeting in Venice. It is to consider now the long-range planning centered around CERN.
I'll hide this the bar. Better.
Okay, yeah. So now you can see the cycle. In the last, since 2012, we've had this cycle. It was supposed to have happened again there in conjunction with and following on the Europeans' plan, but COVID slipped. So, but the pattern now exists, and I'm really happy about that. First, the Europeans do their long-range strategy discussion. It's a big deal now because FCC is the topic of everybody's interest. And in Venice this week is when they're meeting. Hitoshi is giving the US P5 recommendations to the Europeans tomorrow. Then comes the SNOMAS study. Then comes a heat map study, and then we do it over again. Okay. The reason we got into this cycle is because 2008. 2008 wasn't great. There was a heat map panel commissioned in 2008, where a bunch of really good people and smart people got together and came back with recommendations for the field that didn't go very well. This is where we got the frontiers, the circles. As soon as they were embedded into spreadsheets in the agencies, we were stuck with the circles. We kind of didn't like the circles because they were siloing the field in some ways. And not everybody owned that particular set of recommendations. They just kind of appeared. And so we bickered. We actually got into trouble because we had people going to Congress saying, do neutrinos, don't do colliders, and people going to Congress saying, do ILC, don't do colliders. You know, it was a mess. So we had to do something about that. So about 2011, we knew the top data is discovered it's probably coming or not. I was on ECFA at the time, and I know that the Director General at CERN was actually beginning to prepare materials of how to describe it if it wasn't found. That would have been a big deal. We all understand that, but it's sold discovery that it's closed. So anyway, it was time to do another P5. And at that time, I was the chair of the TPS. But I knew it had to be different, and we had to think like nuclear physics. Those guys over there, their long-range planning was always great. Everybody bought it. They had a mechanism of connecting the advice to the government with a broad community activity. We didn't do that. We in fact relied on laboratory directors often to kind of direct our advice. So we invented a process. Adding it right followed me in the chair line, and we convinced DOE and NSF that we should commission snowmass. There's a story there, you can ask me afterwards, it's a sad story, the reason we call it snowmass. A process whereby the community would get together and think about the physics without any constraint on schedule, personnel, calendar, just what's the best physics to do. And then find a way to plug it into HEPAP, who would then use that as data to produce actual recommendations that the community owned. Well, it worked really well that first time. We started working continued the themes of frontiers, invented a bunch of other frontiers for study purposes. If you're a theorist, you might note that there's not a theory frontier. That was a huge mistake. We argued about it in meetings at the O'Hare Airport that we had every 3 weeks or something. So we were trying to build that airplane while we flew it. I missed a meeting somewhere along the line, and so I ended up convening the Energy Frontier part of this with Michael Pesky. And so that was a year-long study. It created a report. We did it right, finally. And then we did it again, 2021. Another report. This next NOMAS report. Our themes were those. The most recent P5 did it right. They separated out between the processes. And they added theory frontier. So this was much better, and they did a much better cross-correlation of one frontier with another, because they're not isolated objects intellectually. And we call them science drivers. They kind of kept them. They just gave them a fancy name and their own little icons of these are the things that drive our field. And if you divide them up into the frontiers, guess who has its own frontier? Physics still does. So we took a lot of victory laps over the years for the success of the standard model, and rightfully so. It's a pretty thing when it's not being really. If you're a historian, you know that something special happened between 1967 and 2012. And if you're from Detroit, you know that it was because that was the second time that Crown winner in baseball, was able to have the highest batting average and the most home runs and the largest number of RBIs. Very rare thing to do in baseball. Well, maybe that's not what we're talking about. We're talking about what happened in 1967 when I was a junior in high school. Steve Weinberg wrote a 3-page paper that defined everything about the standard model that we use today. The same language, the same approach. You can read it today, it makes sense. And of course, in 2012, we culminated what was in that paper by finding the Higgs boson. Okay. What's a big view of the standard model? Well, it guided research for decades. Told us what to look for. We knew the path that we were on. That's cool, but it's also led to a kind of a culture and an expectation of our field of how we work. You kind of have to know the answer before you propose an experiment. It made 3 predictions. The standard model predicted that the weak electromagnetic interactions originate the same theory. It predicted there would be 3 spin 1 vector bosons, 2 of which would be massive. And it predicted a spin 0 field and its excitation could exist. And those are all coupled together, those 3 predictions. Okay, the first one, the weak electromagnetic interactions originate in the same theory, beautifully shown at Hera, where a charge current, neutral current of electromagnetic interaction and a charge current weak interaction at very small distances have the same rate, same strength. At the other ones, I mean, my goodness, this is bread and butter physics is now the Z. It's a point of calibration. You know, yesterday's discovery is a calibration point today. The third one is the beginning of the story. That ended on July 4th, 2012. Peter Higgs was discovered at the at CERN, sitting in the 4th row. That's Fabiola, who was Reinhardt and my boss at the time, and she was the spokesperson of the Atlas experiment. And of course, Higgs died a year ago. So this 2012 discovery seemed to culminate and complete a 40-year-old effort. These days, I can't, this is a joke. I can't. No, it was joking anymore. It's a big deal. We got a lot of praise for this, but we're schizophrenic about this thing. The stakes are really high. When the standard model is good, the standard model is really good. And when the standard model is bad, it's really, really confusing. Let's go back to electricity and magnetism. Standard model of electricity and magnetism. Maxwell wrote this theory in an unreadable form during the American Civil War. It was fixed to the form that we like it, but not until almost 1900. Waves were found that kind of confirmed the idea. Zeeman and Lorentz began to think about particles of electricity. The electron was discovered by JJ. And then industry took off. It was marvelously successful, that theory. And it was riven with crisis, which everybody knew at the very beginning, if you were a theoretical physicist, that there was a major problem. Electrons interact with their own field. That's bad because it leads to infinities. In fact, Oppenheimer cut his teeth originally on calculating quadratic ultraviolet divergence in self-energy of the electron. And it didn't take for a number of years to figure out why that didn't seem to work. Because it's industry, for crying out loud. There's something wrong with the theory. And it was a weird state of schizophrenia. success and catastrophe simultaneously coalescing in history. Well, Terracio's equation in 1928. A few years later, Anderson discovered the positron. That was sufficient to tame the theory. The fact that there is a negative energy state, a positive energy state, makes the self-energy of the electron coherent and finite, and even protected by theory. We'll talk about that later. And then the Lamb shift occurred, and Shelter Island, and well, everybody got together, the hoo-has of the field, and figured out a way to describe all this, and Kate Feynman and the Feynman diagrams and all the rules. But again, a whole bunch of people had good ideas about combining theories, describing things. The W and the Z were found that seemed to confirm things. The Higgs boson phenomenology that came in a kind of a form of a Bible that everybody followed, followed much later. And it was clear that the standard model was amazing, but it's full of crises in much the same way. Success and catastrophe sort of going hand in hand historically along the way. We're still working and waiting for our land shift Shelter Island. Okay, the standard model ingredients were something called the gauge principle, which was invented a long time ago by violence. It demanded a symmetry and spontaneous symmetry breaking, sort of out of left field, a description of phase transitions. Two of those go together. Now, what's the particle physics periodic table? You know it. You can count it with 2 hands and 2 feet, the number of particles in the theory. We know them. They're constrained in a particular pattern by the group structure and observation. If all we're doing is counting particles, we're just doing standard collecting. Obviously, it's got to be one, namely how the particles talk to one another. You know those as the spin 1 bosons. I call them the messenger fields of the field of the strings. And maybe in some ways even a Higgs flux. That's what we're playing with. But they go together in ways that are really opposite. There's a scale that's important in the theory. It's close to these highest mass objects, which everybody keeps thinking has to be important. That can't be a coincidence in any case. The masses are insulting. We ought to be able to understand what in the world that many orders of magnitude differences among the masses. So what's great about the standard model is, in fact, the gauge principle. It's a really pretty idea. It asks, what kind of theories will accommodate a particular kind of symmetry? With a transformation that's one mechanical looking, but it's also theoretic. You can have a global transformation. You take every wave function or operator in your theory and you shift it by a phase. Not all combinations of those operators will preserve that. And so that's a way of limiting the number of ways you can put symbols together. That's not very restrictive, at least with regard to conservation of light. Or you can insist that every wave function at every space-time point gets its own phase rotation. That's very restrictive. If you're going to demand that of your world, then the number of ways you can put symbols together in a Lagrangian are limited. And it's kind of magic, as you've heard, and probably already knew, because the demand of that kind of local symmetry forces a spin 1 field to exist. Not only that, it forces the way in which that spin 1 field interacts with the matter fields in your theory. Think about that. The demand of a theory forces the creation or the existence of a particular kind of particle. Not only that, it forces how it interacts. I have a baseball analogy for gauge invariance, so ask me afterwards if you're interested. So the gauge principle unfolds rather neatly in the standard model to just these equations. The kinetic energy terms describe a whole bunch of interactions of in one fields, and the interaction describes how they work with matter. And it's great. It is the most accurate way that humankind has described the world ever. Highly precise. Great for us. It's a standard model. Model's a simplified description. It's not a dynamical theory. Here's what I mean. Everybody needs a hobby. My hobby is orthopedic surgery. I've had 14 of them. Due to a football game 100 years ago, I've had 12 knee surgeries and 2 hips replaced. Yeah, I could build you a model of how you walk with springs and pulleys and rubber bands. That'd be an effective theory of walking. It's not a dynamical theory of walking involving muscles and ligaments and tendons and bones. That's the difference. Walking is the result, but the model used to make walking happen are very different. Standard models an effective theory. And then there's spontaneous syndrome. That's the story. How do you get it? Well, you write down this really nice Lagrangian that Weinberg writes down for you. You get out your pencil, you get out your pencil, and you do a silly thing. Change the sign of white ring. Boom. Standard model and the universal limit. That's not new. We know that kind of model. It's the model that describes a whole bunch of second order phase transitions in materials science. Like a magnet. When a magnet is really hot, the free energy fluctuates around zero. Its average energy is zero. And the potential energy, that free energy, is described as a quadratic. Turn off the heat, all those spins go in one collaborative direction. Magnetism comes into being, and the free energy gets another term. The order parameter of that phase transition is the magnetization. The magnet finds one of, in this simple case, 2 possible ways to have a finite value. Okay. Oh, yeah. Here I have a magnet, a very pure hunk of iron attached to a magnetic field. Let's heat it up. When the iron gets to about 1,000 degrees Fahrenheit, 770 degrees Celsius, something magical is going to happen. We're about to see an example of experiment theory collaboration. Because my TA here is going to take. See what happened?
That's what happens.
Now, TA, now. See what happened? Take it from me. Okay. When it lost its magnetism and then it regained it. That's a metaphor for what happened in our universe. When there was no magnetization and this thing was hot, that's the Big Bang right after. The concept of magnetization does not exist when that is above the Curie point. It was Pierre Curie, by the way, not Marie. Then it cools and it undergoes this volume-wide, all at once, second order phase transition, breaking that symmetry. Now magnetization exists. Now there's a reason for the change of sign in that theory. From these two guys who first wrote it down for superconductivity. Here's the free energy for a superconductor. This is the wave function of a Cooper pair. Notice the square and the quartic power terms. We stole it. Lock, stock, and barrel. We stole it from condensed matter physics. In the standard model, we live in that broken symmetry world, like that one. And what we try to understand is what were the dynamics that led to that breaking of the symmetry. And what is it that corresponds to that sign change of the Lagrangian? So the story we tell us is there's a universal phase transition that occurs. The entire universe was in one state when it was hot, just like that guy. And then the universe expanded and it cooled. And a switch flipped. And a symmetry was broken. Not the simple symmetry in the magnet, something a little more complicated. The equation involves two coupling constants, lambda and mu, which we'll come back to. And a value. That's the 246. So pay attention to that parameter a bit. By making measurements in all kinds of things, we have numbers for these parameters. And the thing about the Higgs that's so weird, you all know that the world is fields, not particles. And you all know that Heisenberg won't let those fields have actually zero energy in the vacuum. Fluctuate around zero, right? Of the Higgs. When the phase transition occurs, the Higgs is on. The Higgs is on 24/7. Everywhere and every when there's a Higgs field. And here's the story we tell ourselves of what happened. In the earliest times, there was this particular minimal collection of spin 0 and spin 1 objects, no masses. Why is that way? Because Weinberg wrote it down in his paper, that's why. It's the minimal theory. Well, as the universe cools, these individual fields condense. And some of these original spin 0 fields combine with some of the previously massless spin 1 fields. You all know that 2 degrees of freedom for spin 1 is massless, 3 degrees of freedom is massive. That happens. These two, that one and that one, mix together. One of these guys gets attached to that, and the remaining one is left without a mix. It was cooked up to be that way in Weinberg's paper. He knew he had to make a photon, otherwise his theory was just meaningless. So he forced the mixing to have a particular angle, the Weinberg angle. You know, there's a certain amount of ad hocness in what Weinberg had to do in order to get to where we are. And of course, what's left over is a spin 0 field. So these two ingredients all are required, and they're all described in Weinberg's picture. And all these guys had something to do with it. And it was Higgs who wrote down the model that was easiest to parameterize. It could just be lifted, and that's what Weinberg did. This guy, we were so mad at Phil Anderson because he fought tooth and nail against the SOC. He didn't deserve the snubbing he got because he had the original idea. He should have gotten the Nobel Prize for spontaneous solution. So what's exciting about the Standard Model? Well, its historic significance. It's apparently a long path of making theories come to a common end. And its job is really special. Particles, charged particles, are massless inherently, but that Higgs field that's on all the time, they move through it. And their coupling with it gives them mass, almost like inertia. So there was some point in the universe when all those things were running around at speed of light, where they now find the Higgs field because it suddenly exists. Mass was born in the Higgs field. So what's challenging? Well, pretty much everything about the Higgs is challenging. First of all, a spin 0 plus field. I know the quantum numbers of 0 plus, just the quantum numbers of the vacuum. This particle has the quantum numbers of the vacuum. It also unfolds into all these terms with the parameters that I've already mentioned to you. So anywhere you see a V, that's the field. And anywhere you see an H, that's the excitation of the field. So all the interactions that I just described, the mass term proportional to field V and its own coupling. Same with the spin 1 guys and the Higgs itself. The rest of these involve how the Higgs boson interacts proportional to the mass that comes from here. Likewise, the Higgs with itself. Likewise, the Higgs with the spin 1 objects, the massive ones. So let's talk about it. What happened? Well, inside a whole mess of background with a not awful cross-section was the Higgs. And of course, it came relatively quickly when the LHC turned on, but that's the second time the LHC turned on. Remember the disaster that had happened 18 months or whatever it was before when the LHC came on, everybody was happy, the experiments weren't quite ready, but nonetheless, we're all happy, and then it broke. And it was down for 13, 14 months. So we were ready by the time it started up the second time. But it's strange. Like I said, it was the quantum numbers of the vacuum. Just think about that. So how many things in our particle physics world are just one thing? Right? Everything's a multiplet of some sort. Not the Higgs. It's an elementary singlet. Or you could think of it as actually a doublet where those other guys are hiding inside the Goldstone as Goldstone bosons. Michael likes to call it a singleton. There's a lot of confusion, and our need is to unpack that potential. There's the vacuum energy, there's the Higgs mass, there's the Higgs potential shape, and there's the fermion loops. You know that you're obligated to deal with loops by integrating over all momenta for all the known particles in a loop and all of the unknown particles in the loop, which is a way of looking for unknown particles. And they're the core of our language. We knew where to look for the top word, as the loops told us. Likewise, we knew where to look for the Higgs boson, because those loops told us. And I'll come back to that. But what about a spin 0 elementary particle? It's got issues. The self-energy of an electron doesn't have these issues. The self-energy electron is multiplicative between bare mass and logarithmic mass, logarithmic dimensionless, not spin zero particles. The corrections are added in quadratic form to whatever the heck that is. And they're dimensionful. So if you add up and just do the exercise, spin half particles lead you to a negative contribution to the correction. Just doing standard quantum mechanics and the spin zero object or the Bose-like objects give you positive contributions. Which means that somehow this guy, whatever the heck it is, has to balance, be thrown in there to balance because the Higgs mass is too light to make sense. This is called the hierarchy problem. It's called unnatural because it's got a buzzword sitting now under attack in various quarters. The next scale or the Planck scale, and the kind of subtraction that's required here is like that. I don't even bother to count the number of commas. Is that a coincidence? Seems part of the picture, right? And what you like is that, first of all, that this is making a hint and that all the unknown particles go to balance that out. Then it looks more like normal particles. So we kind of figure that about a TeV for new particles is what's required. So we look for new physics of the TeV scale. And there are a whole bunch of models that lead to that kind of thing. This is nice. Cooper pair, described by Ginsburg and Landau. Right? What's a Cooper pair? It's a macroscopic combination of two electrons in a superconducting material that form a Bose object, a quasi-particle that in fact oscillate and create fields that expel a magnetic field, the Meissner effect. The Cooper pair is a composite quasi-particle made up of two things. That expelling of the magnetic field in a classical way, that describing that leads to a massive spin one equation. If that doesn't work, then we find ourselves in a strange place. That's just the way it is. That's a better term for that in my mind is that's giving up. Or we lead ourselves into all kinds of strange places. And then there's this issue. You all know the couplings run. And that one runs with scale. And if you calculate the beta function, integrate the beta function for that coupling, letting all the other functions, including the top torque mass, run as well in a scale where our little Mexican hat potential is way down there, this lambda goes negative. That's got to be an issue is the theory. So it's weird. So there are three things to do in our research program. Measure the property of the Higgs boson, the collider program, measure the properties of the top and the W and the Z because they're massive, and so they talk to the Higgs most readily. And of course, search for multi-TeV particles. All right. What are the possibilities? Is the Higgs by itself that minimal model? Is it part of the family like every other particle ever discovered? Does it differ in really tiny details from that original Higgs that we all now know and love? We have to measure it in every way possible and as precisely as we can. Here's the golden channel. You all know about that. And here are the values of the Higgs mass as measured. Incredibly precise. so far. Growing in time. These, like well, that's the Z in 4 leptons. And here's a more recent version. Incredibly precise. How about the couplings? Well, the couplings, it's a slog. I know theorists don't like kappa, but we use the kappas anyways. The idea is they appear in production and they're constrainable by measurement. And of course, what we're looking for is for one of them or some of them to not quite be in line with what the model would be. Oh, well, depends on your model, but again, it's sort of a percent to some percent, to begin to really flow that, but then we'll have the other models that might be used to describe this thing. And it's happening. This is incredibly precise again, but we're still at the sort of 5% level. In the 2013 SNOMAS, we erected this diagram of the expected precision for a variety of machines. And here's the high luminosity LAC there. And I put on here the 0.5 to 5% precision marks that we sort of thought was reasonable. And I was happy to see that those numbers have still pretty much held up. So we're not doing rocket science here. And it's the same for all the other couplings, except the K capacity. Electroweak physics, well, there's the WMAS, all the more WMAS. You heard me say a couple of days ago that CDF measurement, that was heroic. The amount of cross checks that they did blinded, really amazing. From a collaboration that hasn't gotten together in 15 years. That's because Ashutosh Kotwal is a magician. CMS, we've been waiting for CMS to come out with their measurement, and they did, and it's right in line. But hey, here's my own personal bias. Precise measurement, they might have liked them to be on both sides, right? And there's that guy, and there's that guy. Okay, these are the observables that I used to call the Fermilab observables. The plot of the mass of the W versus the mass of the top. That prediction is a logarithmic function of the Higgs mass possibilities. So measure the W mass, measure the top mass. That intersection should lead you to an expectation for what the Higgs mass should be. And here's the famous plot. Notice, this is a brutal measurement, the W mass measurement. I led the first D0 W mass measurement, and I'm proud of 2 things. First, I'm proud of the fact that we got a value that led to some controversy because it was higher than CBS. It is kind of higher, everybody's kind of higher. Yeah. And the second thing I'm proud of is we got through that whole project without a single homicide. And it was not at all obvious that that was going to be the case because, wow, ask me afterwards. And there's CDF. Now everybody makes a big deal about CDF being 7 standard deviations away from the theory. It's sort of 3 standard deviations away from other measurements, which remember the LHC measurements are kind of nuts. I don't know. We'd like to do it to 5 MeV, which is just terrifying me. So I think we're going to be able to do that. But imagine if it starts to populate again, kind of at both. So again, top quark. Remember this? And this? That leads to that. When the lambda turns negative, then the potential shape changes, goes away from the going up to going down without bounding. Is that a theory that you're ready to bet your house on, that it has that kind of behavior? So we'd like to measure the top quark mass precisely. Right, I just told you where we are. We're doing it precisely. we wanted to keep up with VMW precision and that two-dimensional plot. It's obviously a fundamental parameter. It holds to the strongest, but it is also a part of this potential problem. If this downward forever shape isn't the way the world is, then something turns it over. And it turns it over either into a state that's like metastable, where that ground state is lower than the moment above, or a state that's stable, meaning it's up higher than no ground state we know and low. So you can imagine there's a whole industry on calculating what kind of models give you what kind of shapes. And there's this plot, which is old. What we'd like is to be able to get the top quark understood as something on the order of a pattern. You know, Reinhardt, we showed you the Monte Carlo measurement of the top quark is already sub 500 MeV. But the theoretical uncertainties, or whatever in the world you call it, when you're trying to decide how to compare experiment to what you'd really want in order to make a sophisticated theoretical comparison, those are of order 500 MeV. So there's work to do to try to understand how to go from measurement to something you might use in a sophisticated calculation like that. This has been redone most recently, still there. Suggest metastate. There's a hint. Oh no. So just a kind of physicist. The top quark has the mass of a uranium atom. And that Monte Carlo measurement is indeed very precise. And this is what I think what Zach was talking about is that difference from the tevatron measurements and the LAC measurements are sort of in tension now for all the reasons that Reinhardt mentioned. And that shape, oh, you can find all kinds of shapes. Actually, CPUON is an author in this paper. So we're chasing lambda as best we can. Here are the ways in which we can measure kappa sub lambda through all the different decay products. Some are background conflicted, like high cross sections. Some are low background, but rarely produced. That's a theme that you've heard before. These are the ones that tend to get the most talk. And there's also a single Higgs way that approach to capability. We used to say this was a basically impossible measurement at the LAC. 2015. We extrapolate, this is an Atlas extrapolation. We think it can be between -4 and 12. Well, here's a measurement of one channel a couple of years ago. And there's that ritual extrapolation. We're already impinging on the it's impossible conclusion. That's because data always make you smarter, and because we keep doing this, we're always so conservative as to how we extrapolate how well we can do with something. The Atlas in particular. Anyway, in 2018, the European strategy people said better than that. And in 2022, Atlas is again saying better than that. And we used to say this is where this 50% came from that you sometimes heard this can amount to nearly impossible. Well, we're already beginning to hit on that. So maybe we're going to do a lot better than we expected. So obviously the Higgs boson program is the philosophy. Path beyond the standard model. All the ways in which we've surprised ourselves since Rutherford. Compositeness, as I've already swooned about, maybe the Higgs is composite. Expansion of the gauge groups, new families, sure. Beyond the standard model, we get motivation from all of these things in my mind. The TEV scale, yeah, I'm afraid we're passing the TEV scale in many of the exotic searches that we look at now. Okay, what about the future? 12%. That's a number. That's the amount of data we've taken at the LAC of the approved running. Another way of saying that is 88% is how much LAC running is to come. So here's the history of the LAC running. Now we're there. And run 3 has been extended because neither the accelerator nor the experiments are ready for the high luminosity LHC upgrades that are extensive. So by the time we get to here, yeah, I'll be sitting on a porch. Okay, 4 things to my thing 1. Mass. We collider types. We keep saying in the media, everywhere we go, in the elevator, to my wife before we turn out the lights. We know about mass because we figured it out. As long as we don't know anything about the mass of any neutral fermion, or, oh, by the way, about 85% of the gravitating universe, we don't know mass. Neutrino mass is true on the standard model. Weinberg wrote his paper. We've continued to use the ideas for a massless neutrino with a SU2 left plus U1 gate. Think of the ways in which you know a spin 1/2 object has to have a mass. It has to have right. Well, if it's just a direct kind of mass like an electron, then doesn't that mean there probably needs to be somewhere in the theory? It's not entirely the case all the time, but the simple-minded way, an SU2 right. Isn't that another way of saying there's probably got to be W rights to be found? And a different big structure. You can just throw in U1 right-handed components to the isn't that seesaw of 1? We don't touch the Higgs structure to do that. But then there are other ways that do compromise the minimal Higgs structure. A Majorana mass of some sort, whether it's seesaw or not. I don't know how to make a mass out of that looks like the kind of mass generation that we know and love for the charge fermions. So my contention is that this is brand new physics that even affects the LHC tension. That's a big hit. Circles. Bumper sticker frontiers. Well, they're pithy now. I'm with that too. But where's the new physics going to appear? Is it going to appear just in the energy frontier, or just in the neutrinos, or just in the cosmic side, or just in the where? Isn't it kind of likely that if there's new physics in one, it's going to affect the other? That's even true for neutrino masses and cosmic cosmological issues. How about theory? The precision frontier. Have you remembered, did you notice how big a deal this was in almost all of the talks that you got? The compromised way in which during experiment we're going to have to struggle to keep up with one another in precision. it has to be the case, otherwise the mission of the LLC is so not going to be as fulfilled as it could be. Because we're going to continue to just understand our detector to explicit precision, statistical imprecision, for only a few kinds of interactions, the statistics going to diminish. But it is going to be something. Here's a plot from Atlas of various cross sections. The gray is theory. Our sons and our children. And same was true for this famous plot of all the cross sections. Theory matters. The game is becoming, it started out being, I'll pick my model, I'm going to search for it, not get it. I began to think that after a few years, if somebody found a signal, that would be a disaster. Because our entire culture is setting limits. But we've got to be able to say that's new physics. So there's a lot of out and out theoretical calculations that need to be done, phenomenology that needs to be done, and modeling that needs to be done at a level that we've only imagined up until now, in order for the LIC program to be a success. So here's the punchline. I said, here's the punchline. It is particle change everything. Even if you work in neutrino physics, the Higgs particle changes everything. Standard model guided our research. We don't have that anymore. The road is unguided. We're either completely unconstrained or completely constrained, but we don't know what's out there. In the first time in my professional career, we're unguided. We're exploring. Much like a telescope explores. That's never been the way we did things in 45 years. Just exploring. And isn't that sort of the very definition of following the frontier? Thanks for your attention. I want to say something. This morning we learned that Sophie got her first DOE grant. I think that's cool. In these crazy times. Yeah.
Very good. So questions?
Yep.
What's the baseball analogy?
Okay. Baseball teams tend to wear the same color uniform. Rules don't depend on that of baseball. Suppose you had a team that was rogue, the Savannah Bananas, except they still also wear the same color uniforms. Every player dresses in the first up, the way they want. And they change throughout the game. Okay? Think of the color of their uniforms as a phase. I coached high school baseball for a number of years. This would drive me crazy. We'd be doing polls if we had that kind of thing going on. But this manager spends the game going from player to player and adjusting the phase of each player, keeping them all conserved. That's the photo. The manager is the photo. And the job of the manager is to keep the phases in mind. Can't have that concentration, that local symmetry without command, without a spin one team. That's the analogy. That's Kerry Winston.
Very good. Other questions? Awesome. So why is the Higgs potential so simple? So that we kind of live at exactly at the Curie temperature. Yeah.
And it couldn't be simpler. That's the other thing that's astonishing, is the very first simplest thing you can write down is the one that seems to be the way the world was. That's obviously not a reason to dislike it, but isn't it curious?
I like the top mass thing. I'm glad you brought it up since I did. I always think of it as a little more intentional. Our measurement of the top mass determines when the universe will end.
Yeah, yeah. And we don't know how to make that comparison properly. Monte Carlo mass is not the right thing to use. That phase diagram.
And that Temperature promises an earlier demise.
That's right.
But that same kind of argument calculates the expansion of the universe, cosmological constant, incorrectly to 120 orders of magnitude. That same argument.
It's so much true. The worst prediction in physics. Do you understand why tell me why the discovery of positron fixed the mass correction for the electron crisis? No one wants that?
No, it's taught in the relativistic quantum mechanics. Yeah. But that also hint. It's also it told us that there is no real emptiness of the world.
Here's how I think I understand. Here's the diagram we're talking about, right? Right? In order for this to be sensible, the correction of the electron mass sort of goes like, there's an alpha, there's a bare mass, there's a log of a scale. When you calculate that, out here, you've got, if it's an electron, you've got the positive energy space. What do you do in the loop? In the loop, you're obligated to sum over positive and the negative energy space. That's where Oppenheimer fell, because he wouldn't have known this kind of thing. It was only 4 years later that Beta actually figured out the logarithmic nature. So without doing that complete summation, you don't have this nicely controlled correction, which is multiplicative. Like I said, Higgs is additive. It's a single power of a mass instead of the goofy square of the mass. And it's dimensionless in the scale, where the Higgs correction is dimension-full in the scale. So that's why this is so bothersome to people, is it's not at all the QED we know and love, and the control that we know and love of how to deal with relativistic corrections.
Is that right?
Yeah. He also tells us that it's well, in principle, this theory is not sufficient for precision measurements. So because eventually you could say you could predict the nature at these scales in terms of the parameters of fundamental scale like the Planck scale, but there is a large cancellation there, which tells you that you cannot predict nature across the full range of energies.
And the logarithm blows up as the cutoff goes to infinity. But only logarithm,
only logarithm.
you know, the log of a million is only 6.
Doesn't that say you need more hoops?
Is there questions?
Got a question about your analogy, which I thought was really nice between the electromagnetic, the beginning of the electromagnetic era, let's say,
Yeah,
and how it was going through crisis and achievements and stuff. And the analogy with today's era.
Yeah.
The difference I spotted was that in the first era, there was, you mentioned an industry that kind of helped its inertia.
the one version of Europe.
Yeah, and it helps sort of the public willingness to fund continued research. And I don't quite see that in today's era. What do you think could take place?
You know. You're right, saying this is inside baseball. That we're talking about here, these are some, what I talked about here is our set of nuance, we all come and understand it. Now put yourself in an elevator with a congressional staff on this plane. It's gotta be in a building that's much higher than any building you see.
Yeah.
It's really complicated stuff. And one of the great things about us is that we're smart and there are lots of us, and lots of things about us that we all have independence and so we were both. That's what I say crazy things about what we're going to do. And what we could, you know, we're fixing the universe, you see that. I don't know the answer, but that's why the process has been comforting to me. Right, because now we're in a mode where the community really does use sophisticated stuff. It looks at the SNOMES documents, either one of them. It's serious physics. And the government's willing to accept that the panel of experts that they convene can absorb that and make the right decisions. So we don't have to have public in some lobbying sort of way, and that's the way it's worked. Holy cow, I don't know how well that's going to work. Because the way the budgets are done, we're way below the lowest expected scenario that D5 was asking. So that's what Atoshi is talking about. More probably going to have another P5 with a different set of budgetary constraints to work with. And now we'd be getting into aggregating it. You know, that's how we work. We build stuff a decade in advance, right? The LAC job, that's how many jobs you develop. Dunes construction is handed out. The United States is deeply embedded in producing things. But if the budget cuts are severe, I don't know how we do that and maintain support for the scientists who are necessary in the experiments. Because when state departments are involved, it's going to be meeting the obligations. Secretaries of State and some. I don't know if the public can help with that access. I like science. I'm talking to my reps. Not my reps, you talk to your staff. I mean, they've got to have a face of what's going on and what it means. To the White House and the food.
So actually, there is another theme that is also emerging in parallel. And I think I already mentioned to you that if you ask a statistician what happens right now with science, they say that now science moves beyond the 20th century science, but it moves towards science with large data sets, with very complex measurements. And we don't know how to properly interpret our data. So when we have many parameters, so the interpretation of these parameters is different from what we used to. And so now, of course, as particle physicists, we really believe that we measure fundamental parameters of the universe. We have open data sets, but we also use these advanced techniques like CyberTraining that was describing extremely powerful, except I think if we really would like to understand these issues, we really need to develop a new kind of science, instead of statistics. And so there is this additional aspect that our experiments are extremely unique in the sense that we do these measurements that are open, and so they are shared, and you can really try these new techniques to understand and kind of get really to the bottom of our understanding of fundamental parameters and create the knowledge that will be shared by the whole humanity essentially. And that's also a great training ground for young people. I think it's something that comes together with our exploration of fundamental laws of nature.
You just described a huge multi-disciplinary project.
Yeah.
But for example, that's what, if you listen to the CERN colloquium about 2 months ago, so that Yoshua Bengio, who is one of the kind of founding fathers of the AI. So he says that maybe you need to use CERN to develop a new kind of AI called scientist AI. And so he really tries to start this project that basically will involve us physicists, but also involve this kind of new ways to think about, well, essentially natural experiments. And so using this very complex, but also powerful tools.
Yeah, that's kind of something that I was thinking about when I asked the question. I think CERN has been holding the invention of the internet over the public side for quite a while now.
Used to be a positive thing.
Yeah. But I think most of the public sees that as a leverage, so to speak. They're happy. Everyone uses the internet. Society does it. But if you can make a product like something that comes from machine learning or that is similar in leverage to the public, then you increase your chances at least that you'll get senators.
Yeah, the problem is that we're so. There were 2,000 of a single country, that means there were 2,000
Okay.
independent agencies, each with their own units and ways of saying this. What we don't have is, I'll say.
Okay. Well, more questions or? Okay, well, let's thank the chief again. Well, I also would like to thank all lecturers at the CTEQ school, and I think we have several here, and so I think not everyone will be for the remaining 2 days. Right, so therefore, if you'd like to talk either to today's lecturers or then is use this opportunity now, because the next 2 days will be focusing on the conditions. Thank you. I think the showers are developing, so you look at the map. Dicey right now because of the shower, but again, yeah, okay. So you're welcome to go to the White Nuts game and see if they were at the same time. Okay, thank you.
Always goes to the same. Yeah. Very good. So before would you share the slides with us?
I don't think what I sometimes do with stuff like this is make a movie out of it, you know, because there's so many of them. Sure. It'll either be 500 slides or I can just.
So the other thing is that we can put a post recording of your lecture instead of slides, but it will take a day.
Yeah, so you know, again, that was certain,
Oh, yeah, yeah.
generic.
Really?
Yeah.
Even so,
Right. Yeah, no,
What's the next one? There's two different ways of having. I don't want to go through all of it, but I will think.
Well, basically just introduce.
Singles.
It's a smart,
Right, but the relation of the.
Well, we would expect,
it's a window.
That's our new.
not to come and think of it.
It's not, it might sound. Go, it's all around, all of this, like,
There are actually, if you, a number of different questions. So. Doesn't matter. It's in your. Where you not have.
And that's where the. Okay, you don't have 5 cents, I can't say it. Oh, they would.
This I know. And now you're using, yeah, that portion, that type of.
But it was not something really about us. Like interest.
Well, that means. Yes.
Yeah.
Model. Nowadays, everything is modeling. But if you can fix the model, students generate scales. Right, so this is the changing all the time. Because by far the best resolution comes from having a full final safety constructed. So you need at least one check, which is the bottom part check. And so then we're talking about the various four protect checks. That's a perfect help. Right, but right now, we're still at functionally going with the problem, so carton shower, all those things, and all the different scales. But that's changing a lot since we're already profiling, right, which is a little bit of a difficult situation nowadays, right? Because if you can set up the right system at a concern now, you can profile them down to like 10% of the original value, which maybe that's too much profiling, but you have a great uncertainty on your measurement. They want to. I was thinking about doing